Hi everyone. In this session, we'll cover types of inventories, ABC approach, which is basically used for classifying type of inventories into different categories. We'll also look at EOQ, which is economic order quantity model, and then economic production quantity model, and third one is quantity discount models. And we'll also look at two strategies. One is like reorder point and single period models. So let's start with the next slide. The basic definition of inventory is a stock or store of goods. So anything which can be stored is inventory. And last time we talked about two different types of demand. One was independent demand and dependent demand. So in aggregate planning, we used dependent demand. Now in this chapter, we are looking basically where the demand is independent. So we are looking at finished and ready to be sold goods, raw materials and purchase parts. So that's one type. And then within the company, you have partially completed goods. So maybe an item needs 5 different operations. So if it has gone through maybe first and second operation, and 3 more operations are needed to be carried out, then if it is stored somewhere before it moves to the next station, it is called as work in progress. And when all the operations required on a product are completed, then we have finished goods inventories. There are also inventories for replacement parts, tools, other supplies which are used during any manufacturing. And then there will be some inventories where you have goods in transit. So they are moving from one place to other place, going to the customers. So inventory serves several purposes. Why we need to carry inventory? There are so many different reasons. It is used to meet anticipated demand. So because demand, as you know, especially independent demand, has a lot of uncertainty involved. So there could be fluctuations up and down. And to meet that demand in a consistent manner, like because you cannot change your capacity every now and then, and if you are utilizing the capacity, maybe inventory can be stored when there is excess capacity and when the demand is low, and you can use that inventory when the demand increases. So it is used for meeting anticipated demand, to smooth production requirements for the same reason, like when there is a mismatch between capacity and demand. As we discussed earlier, there are different strategies that can be followed. So one is like you can smooth your production requirements over the period. It could be used to decouple operations. Like it could be you have operation 1, which is needed for a product, and then operation 2, and then let's say to operation 3. Suppose this machine at operation 1 breaks down and it is not available, then operation 2 and operation 3, if there is no inventory available, they are going to suffer because they will be sitting idle. So inventory can be used if there are materials, semi-finished materials available here in the inventory, that can be used and fed into operation 2 and 3 while this process people work on to correct the problems. So it can help basically to keep the show going. The next one is to protect against stockouts. So people keep inventory so that if a customer needs something and if it is not there, then that's a stockout situation. So to protect against those situations, people keep inventory. And similarly, there are so many other reasons one can list for carrying inventory. Now, the main objective of inventory control is to achieve satisfactory level of customer service. That's one important variable, while keeping inventory costs within reasonable bounds. So these are the two important variables while deciding or trying to control inventory. So we are trying to all the time balance cost with the customer service. Obviously, a company can keep huge amount of inventory so that whenever that item is needed, they can provide it from the inventory. But then keeping a lot of inventory is going to increase the inventory cost. So that will bring down obviously the profit of any company. So people always try to have a balance between the two. One of the metrics that is used for measuring the performance of any inventory control process is inventory turnover. Now, this is the ratio of average cost of goods sold to average inventory investment. So, cost of goods sold divided by average inventory investment. So, obviously, this is higher the better kind of characteristic. So, you want this number to be as high as you can. So, that will basically indicate efficient management of inventory. Sometimes people also look at days of inventory at hand. That also is a good indicator of performance. Any effective inventory management, it needs certain things. There are certain requirements. So one is a system to keep track of inventory. So there has to be a system which monitors or tracks what's available and how things are changing. It also needs a reliable forecast of demand because we try to keep inventory to fulfill a demand. So if the demand forecasting is not accurate, then whatever inventory management we are trying to do will suffer. Knowledge of lead times is also important because if we place an order to a supplier and if the lead time is known to be 2 days, but in fact if it takes 3 days, then that's going to be another problem. Reasonable estimates of holding, ordering, and shortage costs. So holding cost is if inventory is kept, so obviously it will cost some money. So it will occupy some space. It may get damaged. There could be some insurance costs. So all those things are incorporated in the holding cost. Ordering is every time an order is placed with any supplier, that process is going to cost some money. And then the shortage cost is if customer is looking for something and if we cannot make it available to the customer, so there is a cost involved. The customer dissatisfaction may result. Maybe that customer doesn't return in future. And what also is needed is a good classification system. So we are going to look at each of them in more detail in next few slides. So coming to the first one, which is inventory counting system. So there is first one, which is periodic system. So as the name suggests, physical count of items made at periodic intervals. So this interval could be in weeks or it could be months. So it depends on the situation. Then there is a perpetual inventory system. So system that keeps track of removals from the inventory continuously. So every time any change happens, it is being tracked. So thus monitoring current levels of each item. Like one good example you can think of here is bank deposits. Every time we deposit money, obviously we want instant information. We can look at on the internet and then see that the money has been taken out, went into the system. You don't want to wait like a month or 6 months just to know that, otherwise there will be some confusion. Another system which companies use is two-bin system. So this is a very simple yet very practical system. So what happens is there are two containers of inventory, and as soon as one of the containers becomes empty, that's an indication that a reorder has to be made for that part or component. So a purchase order is sent as soon as one of the containers is empty. Now, what should be the size of the container, how many items it should include, that depends on the lead time. So the second container should have sufficient amount to meet the needs during the interim. So let's say if it takes 3 days for that item to reach the company, then during those 3 days, we should have sufficient items in that second container. People also use universal barcode for monitoring and controlling inventory nowadays. So barcode, as you know, is printed on a label that has information about the item to which it is attached. So one example, typical example is given here. So if you look at the numbers, 0 here means grocery. Then second set of numbers, they relate to the manufacturer. And this third set is the specific item. Nowadays, some companies also use what is called as RFID, radio frequency identification. So as the name suggests, this system basically uses radio waves to monitor different products. And the good thing about RFID is that you don't need a direct line of sight. Like to scan barcodes, you need direct line of sight, but not for RFID because they use radio waves, and for that you don't need direct line of sight. One example of use of RFID, it can measure the temperature and give that information on a continuous basis. So it can monitor a temperature of maybe fruits. So that could be something very useful. Coming to some key inventory terms you may come across. The first one is lead time. So this is the time interval between ordering and receiving the order. So if we place an order today to a supplier, and if the items which we ordered reaches us in 3 days,
then the lead time is 3 days.
Holding or carrying cost. So cost to carry an item in inventory for a length of time, usually a year. So this is one of the costs involved in inventory. Ordering cost is the cost of ordering and receiving inventory. So all the paperwork maybe which is involved. Probably it could have inspection also, like incoming inspection. So all that is part of ordering cost. And then the next cost is shortage cost. Cost when demand exceeds supply. So if the customer is not able to get those items which the customer needs, so there is a shortage, and that can involve some tangible and also intangible costs. ABC classification system. So this is classifying inventory according to some measure of importance and allocating control efforts accordingly. So obviously it is not feasible for any company, even not only big companies but even medium-sized companies, it's not feasible to monitor each and everything and by giving it equal priority, because different items could be different in value and they could have different significance. So it is important sometimes for practical reasons to classify them in different categories so that different priority can be given to different categories. So in ABC system, A is considered very important, B is considered moderately important, and C is the least important. So like in manufacturing, C could be nuts and bolts, small nuts and bolts, and A could be more important components. So if you look at the chart, so you can see the percentage of items on the x-axis and dollar value on the y-axis. So there could be items which are classified under A which have low percentage in terms of numbers, but in terms of dollar value they may be highest. So they are classified as A. On the other extreme we have C. Although they are many in number, but in terms of dollar value they are not very high. One good thing about ABC classification is that you can give different priority. Like if a company is using a counting system, they should count more of A items and spend less time on C items. So one of the applications of ABC concept is cycle counting. So a physical count of items in the inventory. So each and every item is confirmed and verified. Now, people suggest a good time to do physical counts is when the inventory levels are almost zero, so that the counting process will be, one is it will be quick and also it will be very accurate. Cycle counting management. So in that one needs to know how much accuracy is needed. So obviously if it is A category of items, so accuracy requirement would be much higher compared to a C category. Second one is when should cycle counting be performed? So one example I gave was when the inventories are low, or when a company is trying to reorder because the inventory is not there. Other situation could be when there are some problems. So if some parts are missing, or because of that, if the assembly is suffering, so whenever some problems occur, it is a good time to verify all these things. Other one is who should do it. So it has to be, especially if the products are very complex, not everybody can be involved in doing this kind of inventory management. So it should be people who are trained, well trained to do this particular activity should be involved. There are different inventory models which companies use, and a popular one is EOQ model, economic order quantity. So within that, actually, there is a basic model, basic EOQ model, then there is a EPQ, economic production quantity, and the third one is quantity discount model. So the main purpose of using these models is you basically want to minimize the total cost. So let's look at some of the basic assumptions. So they assume only one product is involved. So this is for simplicity. Annual demand
Requirements known.
demand is even throughout the year. So we are not looking at a very high amount of seasonality. Lead time does not vary. So we should not have a situation where lead time is 2 days for one supply, and for the same supply next time it becomes 1 month. So we are not looking at that kind of high variability. Each order is received in a single delivery. So one order means one delivery, and there are no quantity discounts. So if you look at any basic inventory cycle, let's say the order quantity or order size is Q, and it is about 350 units. So at time 0, so here we receive 350 items. Now let's say usage rate is 50 units per day. So every day 50 is being consumed. Now if the reorder point, so this is another term we looked at earlier, is suppose 100. So on the 5th day, if we are consuming 50 items per day, so on 5 days we have consumed 250 items. So only 100 is left. So that triggers a reorder. So a reorder is placed here, and we are assuming that lead time is 2 days. So lead time is 2 days because reorder point is 100. So in those 2 days, these 100 units can be used. And before we exhaust those 100 items, we get 350 on the 7th day. And this cycle keeps on repeating smoothly. Now, if you look at cost involved in any inventory situation, there are two components. One is annual inventory carrying cost. H you can see here is the holding cost per unit. Q is the quantity. So why we use Q by 2? So Q by 2 is the average in the previous chart. If you look at the previous chart, so before the next order comes and from the current period, if starting point is Q, it was in fact 350 in the last slide. So you divide that by 2, that is the average quantity. So put together, this gives us the carrying cost, inventory carrying cost. And then we have ordering cost. So S is the ordering cost. D, as you can see, is the demand, and Q is the quantity. So D by Q, D divided by Q, that basically gives us number of orders. So when you multiply number of orders by ordering cost, so you get total ordering cost. So you have this straight line which keeps on increasing as the order quantity increases, and that is our carrying cost, inventory carrying cost. And the other line is the ordering cost. So as the Q goes up, order quantity goes up, then ordering cost goes down. So let's say, just for an example, suppose demand for a particular item is 12,000. Now if we keep, let's say, Q 1,000, every time we order only 1,000 units. In that case, the total number of orders will be 12. Similarly, if you keep Q 2,000, then the number of orders will come down to 6. So obviously, ordering cost is going to go down as we increase Q. So put together, if you add the two costs, you get the total cost, which is like a U-shaped curve. And the lowest point here is the point where the two cost lines or curves meet, and that gives us Q. So that's the optimal order quantity. So to derive optimum Q value, what we can do is we can say that annual carrying cost is same as the ordering cost. So when they are equal, the total cost is minimum. So now if we solve for Q, you can see if you take Q on the other side, we get Q square equals 2ds divided by h. And when you take square root on both sides, we get Q equals 2ds divided by h. So that's the formula you can see given here. We will work on some problems related to this very soon. Now let's look at the second one, which is economic production quantity. So one thing to remember is that production is done in batches or lots. So it could be lots of 100, 1,000 or 5,000. So capacity to produce a part exceeds the part's usage or demand rate. Assumptions of EPQ are similar to EOQ, except orders are received
incrementally during production.
So that's the only difference. Otherwise, the assumptions are similar to what we had earlier. So if you look at this situation here, you have time on the x-axis and quantity on the y-axis. Now, there are two lines, the solid line and the dotted line given here. So the dotted line indicates if the production was allowed to continue and if there was no usage in between, it would have reached a much higher value. But because it is also being used, you can see production and usage, because that material is also being used while there is a production. So by the time we reach end of this particular period, you can see the quantity is slightly lower. So whatever the difference is, that has been consumed while usage. And then there is no production for the next period. There's no production, only usage. So the quantity or the inventory goes down. And when it reaches 0, again the production starts, and then taking the difference between production and usage, we reach again the maximum inventory level. And then production stops, and then there's only usage, and this way the cycle continues. So if we were to modify the formula for optimal quantity, you can see the first part is exactly same as what we had earlier. The only thing is the next part is something new, where P stands for production or delivery rate, and U stands for usage rate. So one thing to remember here is, although there is no ordering cost, because we are talking about production within a manufacturing plant, we are not ordering anything from outside, but you can think of ordering cost similar to, so because we have used S, so you can say this is similar to setup cost. Because every time we prepare a machine for a run, it needs to be cleaned, maybe some tool change, all that adds up what is called as a setup cost. So that is equivalent to our ordering cost. So for manufacturing or production, S stands for the setup cost. So that's the only small difference. Now coming to the third model, which is quantity discount models. So quantity discount basically is, you can say, price reduction for large orders. So it happens like sometimes we buy something in more quantity, so the manufacturer or the seller is ready to give some discount. So you can see the first two parts are same. Only thing is PD is added, where P stands for unit price. You can see actually in this formula, in the third part, there is no Q. There is no quantity. In the first and second part, you have Q, but the quantity is not there. So what it does overall is depicted on the next slide. So you can see the bold line here is without PD, and then the dotted line is with PD. So it basically pushes the whole curve higher by that amount. So because it is independent of Q and it is constant here, so it just pushes the total cost higher. There is no change as far as the optimal quantity level is concerned. So EOQ remains the same. So total cost with quantity discount. So what happens when there are quantity discount? There could be different optimal Qs. So you can see the lowest cost for the three could be different, because discount plays a role in that. Problem 4. So in problem 4, what is given is you have D. So using the information provided, D is 10,400 packages. So S is $60 and H is $30. So if you look at A, and using the formula we looked at earlier, 2ds by H, you should get 203.96, but we can round this off to 204 boxes. Now for part B, we have the formula for total cost. So using all the numbers, you should be able to get about 6,118.82. Now looking at next problem as an example, number 8 from the homework. So I'll go through 8A. So let me first write down the information which is given. This is 27,000 jars per month. H is 18 cents per month, and S, ordering cost, is $60. So in part A, you can calculate Q using the same formula I gave earlier. So 2ds by H should give you 4242.64, or we can round this off to 4243. You can also calculate total cost with 4,000, so that comes to $765. So you can use the formula for total cost, and then the total cost for 4243 quantity comes to about $763.68. So if you take the difference, you can take the difference here. So that comes to $1.32. Let me also look at question 10. So P is 50 per ton per day, and U is 20, and we have 200 days per year. So what we can do is find D. So 20 times 200. So this will be 4,000 tons per year. Now S is $100, H is $5. You can say per ton per year. So if you look at part A, so formula we had was Q equals 2ds by H times square root of P divided by P minus U. So this gives us about 516.4 tons, or you can convert this into 10,328 bags. Slide 65. So when to reorder with EOQ ordering? So reorder point is when the quantity on hand of an item drops to this amount. The item is reordered. So that's the reorder point. Safety stock is stock that is held in excess of expected demand due to variable demand rate and or lead time. And service level is the probability that demand will not exceed supply during lead time. So this is generally 100 minus stock out risk or chance of stock out. So if you look at safety stock, so safety stock is basically for protection during lead time period. There could be a demand like this as given here, expected demand during the lead time, but maximum probable demand during lead time. So it can also be like this. So to protect these situations, and before we receive the order, there has to be some safety stock so that the customer receives what they need. Reorder point on the next slide. So the reorder point based on normal distribution of lead time demand. So we are assuming that the demand during the lead time is normally distributed as shown in the picture. Service level is considered as probability of no stock out, and the shaded part is the probability of stock out. So you can see this is the Z level. Now if you push this line on the right side, if you increase the value of Z, risk of stock out will reduce. And why it will reduce? Because we will be keeping more items in the safety stock. Because safety stock will increase, so obviously risk of stock out also will decrease. Now one question always is, in any inventory management, how much to order? So there are two models. One is fixed order interval model, and other is fixed quantity model. So there are two different types. So in fixed quantity, you can say the orders are triggered by the quantity. And in fixed interval, the orders are triggered by time. So we are talking about quantity here and time here. As we discussed earlier, when it is fixed quantity, the only protection needed using the safety stock is during the lead time. So the protection is needed basically in this period. So during the lead time, we want to protect. But when we talk about time, the protection is not only needed during the lead time, but also next order cycle. So you can see the protection interval is much larger here. And that's the reason, if you look at the safety stock level, is needed slightly higher for the second situation. Now let's come to the next slide, single period model. So model for ordering of perishables and other items with limited useful lives. So perishables, like some examples you can think of is fresh fruits, or it could be vegetables, it could be seafood like fish, and so on. And items with limited useful life, some examples are newspaper or magazines. Because newspapers become old, nobody wants to read old news, like yesterday's news or maybe 1 week old news. Now, if we start with the first one, which is continuous stocking level situations, then service level is calculated as CS by CS plus CE, where CS stands for shortage cost per unit. Like if we have less newspaper to give, but if the demand is more, obviously there will be some shortage and service level will suffer. And excess cost is if we are carrying, let's say, more newspapers than the demand, then those extra newspapers go waste the next day. So if you look at one problem using this formula, suppose that the excess cost per unit for a given situation is 20 cents per unit, shortage cost is 60 cents per unit, then the service level comes out to be 0.75 or 75%. So using that, you can also say the stock out risk is 1 minus 0.75, which is 25%. So there is a 25% probability under this situation that there will be stock out. So a customer comes looking for a newspaper, for example, and does not get it. So that chance is 25%. So this could be a good metric to see the efficiency or effectiveness of this inventory system. There are some situations where we may not have continuous kind of inventory levels or continuous stocking levels, but it could be discrete, as given on the next slide. So in those situations, these in-between numbers may not be feasible. So this may not be feasible. For example, newspapers, maybe the demand is 10 or 11. It cannot be 10.2 or 10.3. So what we do is we go to the next higher level. If this is, let's say 1, 2, 3, 4, 5, 6. So if it comes out to be, let's say 6.5, we move to 7.